All right, hello and welcome to Lecture 13. Today is all about recursion, which is a very fun topic. But first, let us look at any questions and answers that anybody asked and answer those. And it looks like there were no questions asked. So just remember that this page is always going to be there for you to ask any questions that you want, and I will eventually get to them in a future video. So just know that that exists. And I'll probably be coming back to Safari, so I will leave it open. But let us go now to our slides. So, recursion. We know a little bit about it because we practiced it a bit last time in that factorial function, but let's go in a bit more depth today. So, here are a bunch of images with what's called recursive structure. So see if you can figure out what's going on and how you might define recursion just from these images. So here we have the Mona Lisa, holding the Mona Lisa, holding the Mona Lisa, on and on forever. And here we have, I think it's like a pack of cookies, or maybe it's like instant coffee or tea or something. But the person in this picture is holding this same little tin with the same person's picture on it who is holding the same little tin, on and on forever. And again, we also have these Matryoshka dolls that have smaller and smaller dolls inside of them. And eventually there's a smallest doll, and that is the key to recursion. So remember that. There is always going to be, unlike some of these images that you might see, there's always a concept of a smallest problem when we're talking about recursive problems. So that's some pictures for recursion. Let's talk about some more things. So you can have recursive names. People in CS like to do this a lot. So your compiler is called G++. It's the GNU C++ compiler. And GNU stands for, it's all capital GNU, it stands for GNU is not Unix, so it has its name inside of itself. It is a recursive structure that never ends. But remember, when we're writing problems, we always want our structure to eventually end. And then also there's plenty of recursive structure in these things called like fractals. So here's a bunch of different kinds of fractals. And you know that if you've seen like GIFs of this on the internet, that if you zoom in forever and ever, there's still more to it. And it's still pretty and fun and all that. So that in a nutshell is some examples of recursion. But let's talk about like a definition of it maybe, and how we might use it in CS. It's really important in CS because it allows us to like solve problems by just breaking it down. We're already used to breaking down problems using functions, but this is another way of breaking down a problem into a smaller problem that you can eventually work on. So it's all about abstraction is the idea here. So let's write a few things. So recursion is when something is defined in terms of smaller. I'll put that in quotes because the definition of smaller is up to you. Smaller versions of itself. All right, so that's a weird looking definition, isn't it? And then in CS, we'll have these things called recursive algorithms or recursive problems. And if you've never heard the word algorithm before, your book might say it, or I might have mentioned it in the past. But an algorithm is just a sequence of steps that allows you to accomplish a goal. So any recipe that you write, that you follow, it's really an algorithm. And so we have these things called recursive algorithms, which are ways of solving a problem. These are methods for solving a certain problem. For example, we saw last time the factorial function. And of course, you can implement it in a non-recursive way, but last time we talked about it recursively. And the whole idea behind this is that, let's see if I can like tab over. There we go. Or maybe I can do that. Yeah. So the idea for a recursive algorithm is we're solving some problem, and we want to break it down, a problem, into smaller sub-problems that contain the problem itself. So these smaller subproblems, they're not brand new problems. They are smaller versions of the same problem. How about I say that instead? These subproblems are smaller versions of the same problem. And that is the key. That is the entire key to recursion. You're solving a problem in terms of itself. And that's really weird to think about. And this is a pretty hard concept to grasp. And so the best way that I have found to teach this topic is to just give a million examples. And that's what I'm going to try to do this lecture. So when you are solving a recursive problem, there's always two ways to look at it. When you solve a problem recursively, so I'm going to type a little bit more and then we'll get into real examples. When you solve a problem that is recursive, you have you break it down into two cases. So your first kind of case is what's known as the base case that we've talked about before, and then also the recursive case. Oops. So what do these fancy terms mean? The base case is the smallest version, in a sense, of the problem that you're solving. And you can solve it immediately. You don't need to break anything down anymore. And usually, you're trying to get to the base case, and you're most likely going to start with the recursive case. And that is when you are able to break the problem down into a smaller version of itself. So we were talking about that factorial function. We had the base case where we can immediately solve the factorial. Like 1 factorial, it's immediately 1. I don't have to do any smaller factorials. Whereas if I had some other value, like n, where n was greater than 1, we found we could break it down into multiplying, which we can do in code pretty easily, multiplying n by n minus 1 factorial. And then there was our smaller subproblem, right? And that was the key there. So that was the recursive case, and that was the base case. You can immediately return the fact that, yes, the answer is 1 here. Okay, so that's that. Let's now go back to the slides for a second. So here is just this simplified way of thinking about recursive things. Here's a simplified example, of recursion in real life. So here is a recursive algorithm to solve the problem of washing all the dishes in your sink. Okay, so this is like your function, wash all the dishes. And so assuming we have a giant stack of dishes in our sink, like, I don't know, there's our sink. It's like going down. Got a bunch of dishes stacked up on inside of it. The idea is there's always a top dish on your stack of dishes, and then there's always the rest of the stack, right? And eventually it's going to be empty. So the idea is, all right, here's your algorithm. Wash the dish on the top of the stack. This is your recursive case, assuming you started with more than 0 dishes in your sink, otherwise you wouldn't have called this function, right? So the idea is we found a smaller problem of washing dishes. So here's a smaller stack. Smaller stack of dishes. So that's our smaller problem that we can solve using recursion. So we can call it on, we can call this recursive function, if you will, on this smaller stack of dishes. And all we have to worry about is getting it down to this smaller version of the problem. So in order to break it down, we have to wash this first dish. If we can handle doing just one dish and washing that, then we can break it down into a recursive case where we'll wash the rest of the dishes in the sink recursively. And then our base case is if there are no more dishes in the sink, you can stop. You don't have to do any extra work. There's no breaking anything down. You are done. All right, so that's a simple idea there of that. And so here, it's like to wash the dishes in the sink, wash the remaining dishes in the sink. You should understand that implied in this recursive case is the fact that the dishes got smaller, the number of them got smaller. And so we can eventually know that we're going to get to this case, okay? So I'm going to say something that seems a bit magic now, and we'll talk about that in a second, or maybe in a few slides. So when you write a recursive function, and this is the beauty of recursion, it's kind of magic, but I'll prove it to you, and it won't be magic anymore, it'll be just math. When you write a recursive function, and you call your function inside of itself on a smaller sub-problem, like you're supposed to do, you get to assume that that function call, that recursive function call, does the right thing and solves that subproblem perfectly, without you having to worry about how it's done. So that's really weird. You get to assume that this problem is being solved for you in a sense. And the only catch is, the only requirement for this to always work, this magic, is for you to use that solution to the smaller subproblem. This is a lot of words, it's necessary though. You have to use that solution to the smaller subproblem to solve the bigger one, to solve the bigger problem that you started with. If you can do that, if you can use the fact that, all right, I will call this function on the smaller stack of dishes and assume that that works, and also wash this first dish so that I can get it down to this size of problem, I can guarantee through math that the problem is going to be perfectly solved, and it will be correct. So you just have to worry about using that assumed answer to build up the bigger solution. So this is, I'm sure, very confusing right now, and that is why the best way to talk about recursion is through a bunch of examples. So before we get into any of this, let me just write a bunch of different examples. Let's do, we'll eventually go to code. So let us have another problem. So we did factorial. Let's start a bit simpler now. Here is our problem. I'll call it P. And what we want to do is print the numbers 1 to n. And so that's our problem, and I'm telling you that we can do it recursively. So let's think about it. Let's pretend we had an example. So let's say we want to solve this problem P with the value 5. So this is like print from 1 to 5. And so we'll see on our output screen 1, 2, 3, 4, 5, something like that. So, okay, if I were to call our function, I guess we can call our function P maybe, or print, or something like that, that prints the numbers from 1 to n, where n happens to be 5 in this case. Well, all right, here's our output. Can anybody find me a smaller version of this problem P inside of this? Think about this for a second. I really encourage you to pause the video here, because this is the key. Once you can notice how to break down these problems, you're golden. That's all you need to know. So, if you thought about it long enough, I hope you found that here's a smaller subproblem that matches our problem P for printing numbers from 1 to n. Well, first, if we just solved P of 4, printing from 1 to 4, and then just counted 5, then we would have solved our larger problem that we started with, wouldn't we have? All right, so that could be a good recursive case. And what about our base case? When can we stop? When can we know that there is no smaller subproblem? And you can think about that as you continue to break this problem down into smaller versions of itself. When will you stop? there's two valid answers. There is p of 1 is a valid stopping condition. It's like, okay, we'll just print out 1. We don't have to do any smaller versions of this problem. Or you could stop at p of 0 even, where you just have no output at all. It's like a smaller version of this problem inside of itself where you don't do any output at all. These are valid, both valid base cases. All right, so that's a bunch of hand waving. Let's actually write this down. So here is our problem. Let's call it print 1 to n. Print 1 to n. And so we're given some value for n, and what do? Well, we're going to have to break this problem down, again, into a base case and a recursive case. And we found the recursive case. That's probably the easier one to work with first. So if n is, I don't know, let's say greater than 0, let's do this. I'm just using Python syntax for fun here. It's easier for pseudocode. If n is greater than 0, well, this is our recursive case. And we can break down our problem. So we can call print 1 to n again to solve that smaller problem. We can assume that it works, remember that, on n minus 1. That's essentially, if we were given 5, well, the first thing that we'll do to solve the 5 problem, printing from 1 to 5, is print from 1 to 4. That's a smaller version of this problem. And so we're going to call ourselves, same function name, we're going to call ourselves in the recursive case. That's what it means to be recursive. And then we get to assume that this works. Which is the weirdest thing. So you get to assume that after you call this function right here in the recursive case, your terminal screen, if n equals 5, it now shows 1, 2, 3, and 4 magically. And our job is to use this solution, the one that we get to assume happened for us, to build up the final answer, which is just take what we had, what the recursive solution gave us, and add our 5 to the very end. So we'll see cout n. New line. Yeah? That's the idea, and this is our recursive case. Otherwise, we'll have a base case. And let me be very particular about this base case. Else if n is equal to 0. That's our base case. Well, in that case, we want to print out the numbers from 1 to 0, right? Because that's what this function means. And if n was 0, how do you print out all the numbers from 1 to 0? How many are there? Absolutely none. So do nothing. And that is the entire function. Isn't that interesting? And this is correct, too, which is the weirder bit. So this is a recursive function, print from 1 to n. It calls itself in the recursive case. That's what it means to be recursive. And we get to assume, say that n was 5, that when we call this function on itself recursively with a smaller version of the problem, as you must, it will solve that smaller problem correctly, as long as we build up, using that answer, the correct version of the bigger problem, which involved outputting our last number, that 5 there. Okay? So, let me code this up and prove to you that it works. It's the weirdest thing. But eventually I'll give you some math to help it make more sense. So touch, let's say print recursively .cbp. I'll do both kinds in this one, because we also want to print backwards, and I'll show you that. All right, here's print recursively .cbp. All right, so let's use our favorite number. So I'll say print from 1 to n. And we'll call it with 5. Okay, let's watch it work. So we'll make our function. given an n, and this is going to be a recursive function. And so what it does is it prints 1 new line, 2 new line, dot, 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 new line, n, new line. That's the idea. And all right, so let's break it down. So let's do the base case first, because that's easier. N is equal to 0, do nothing. So if n happens to be 0, just return, and we'll stop the function. And now, otherwise, we're in the recursive case. Actually, I'll show you, there's a bit of an issue if we do it this way, but we'll figure it out in a second. So otherwise, recursive case. And we get to break down the problem. And we already broke it down. In order to do this problem and solve it using itself, we noticed that we had to first call this function on one smaller version of the problem to print from 1 to that n minus 1. It's a smaller version of the problem, that's okay. Call 1 to n of n minus 1. And then also, finally, print n. Because this will get us, assume this works, and it'll print from 1 to n minus 1. Then all we have to do is print n at the very end of it. Okay, that's the idea. So we'll say print from 1 to n, n minus 1. And just to remind myself of the problem, I'll put it there. And then all we have to do is see out n new line. All right? So let's watch this work. So our print from 1 to n function, it's recursive. We get to assume when we call this function, it works automatically. It's kind of like magic, but I'm going to take the magic away soon. And it'll just be understandable and boring, hopefully. That is the goal. But it's still really cool. I love recursion. Make print recursively. My computer's having fun right now doing something. All right. So, what do you know it worked? So, the first way for me to explain why this works is to use a stack diagram. So let's do that. Let's pretend that we called our function from main with n equals to 5. All right. So here we go. Actually, that's way too big of a stack frame. All right, so here's main. And it's going to be hard for me to draw this correctly, but let me just call it print. And you know that we have our one argument. That's our one local variable. It's n. So I can draw a box for it, like this. And it started out being 5. But this, I'm going to write a bunch of diagrams like this. Assume that I mean this when I write something like this. I'm just going to say instead print of 5. It's faster for me to write it like that. Okay? So when I call this function with 5 from main, the first thing it does is it goes and runs it, checks if it's equal to 0, if n is equal to 0. Right now it's not because it's 5. And then it does this call. It's going to say, all right, I know how to solve this problem of printing from 1 to 5. The first thing I need to do is print from 1 to 4. All right, I'll go and do that. Print from 1 to 4. So now print 5 is waiting. It's stuck on this line right here. Print 5 is waiting right here, and then it goes and calls itself. And so now, on the stack, we have another call to print that happened inside of itself, with n equal to 4 in this case. All right? Again, n is not 0, so we'll go to this recursive case again. It's like, all right, I know how to print from 1 to 4. You just print from 1 to 3 first, and I'll worry about after that printing my 4. Okay? Print from 1 to 3. Which again calls the recursive case because it's not 0. It's like, all right, I know how to print from 1 to 3. I'll just print from 1 to 2 and print my 3 at the end of that. All right, print 2. Again, recursive case. I'll print from 1 to 2 by printing from 1 to 1 and print my 2 at the end of that. So we have this chain of function calls going on. It's calling itself, and it's still not 0 here. It's printing from 1 to 1. It's like, all right, I'll just first print from 1 to 0, and then I'll print my 1. And right here is where we hit our base case. All right? And I want to emphasize that no output has happened yet. We just called ourselves a bunch of times, and we have not ever hit all these functions that got to the recursive case. They're waiting right here. They never got to their cout statement yet. But we're just about to unwind. That's the idea of all of this. We're about to unwind because print of 0, that's our base case. All right, it's like, all right, I know how to print from 1 to 0. I'll print nothing at all. Return. Now this is gone, and we're back right here where print of 1 was waiting for this to complete. It's like, all right, I know how to print from 1 to 1. I'll print from 1 to 0, then I'll print my 1. And so it just printed from 1 to 0, did nothing, and now it prints its 1, finally, and then it returns implicitly. So now we have our output. Our first output in the print 1 call just happened. We printed 1 because we finished the recursive call. Now we'll print ourselves. Now back in print of 2 because print of 1 just returned. So it was waiting here to print from 1 to 1. And now I'll print my 2. All right. Print my 2. Then print 2 returns. It did its job. It printed from 1 to 2. Now we're back in print 3, which said originally, I know how to print from 1 to 3. I will first print from 1 to 2 and print my 3. Okay? I'm sorry if me repeating all this annoys you, but that is the idea. That's how I want you to think about this. Just going to ingrain it in your mind. And similarly, print of 4 was waiting to print from 1 to 3, and then it'll print its 4 and returns back to print of 5, which is waiting to print from 1 to 4. Then it'll print its 5, prints its 5, and returns. And what do you know? We're back in main, and we solved the entire problem of printing from 1 to n in terms of itself a lot of the time until we hit our base case. Okay, so this worked, and I just walked you through why it did that. And hopefully that gives you a little bit of insight into why we get to assume that this works, this recursive call to the smaller subproblem, why it works. Because eventually we're going to hit the base case and start unwinding and doing all of this work. And the real work is really this line. It's this c out of n. But the order was guarded by all of these function calls. Okay? So it might seem a bit mysterious still, but hopefully it's becoming slightly more clear. This idea of recursive problems, defined in terms of themselves. And I just want to highlight that it's very important that you understand this right now. It's very, very, very important that when you make a recursive call, and a recursive call, that is when you call a function inside of itself. When you make this recursive call, it's really important that the argument has to be smaller in some way. And that means you're making progress. This guarantees that you make progress towards the base case. And that's when, remember, the base case is when you can stop and you can start unwinding all this work that you were working on. So you have to eventually hit the base case, otherwise you're going to recurse forever, we say, which is essentially an infinite loop. So recursion is another way of looping, because you can think about how you would have written this as a for loop normally, right? So recursion is another way of looping. You don't ever have to use for or while, you could use recursion, and it's equivalent. Isn't that weird? Isn't that cool? All right, I think that's what I want to talk about here. Slight problem, just be very careful about this. Look at what happens when we call this function with -5. It'll first print from, all right, it's not 0. It'll print from 1 to -6, from 1 to -7, right? This is what's going to happen here. It'll be like main, then it'll be like print of -5. All right, I'll print from 1 to -5. First I'll print from 1 to -6, and then print my -5. And this just goes on forever until the end of time, right? Because we're never going to hit 0. So make sure you guard against this kind of error when you call with a number that you don't want. So the easiest way to solve this is make like an invalid case. N is negative. You could lump an n to this, but I'll just do it separately. If n is less than 0, maybe you want to like be error. N can't be negative. And be like, all right, return. Because if you didn't have this, and I ran this, like I said, it's going to be an infinite loop. Oh, yeah. And it'll actually look to be a segmentation fault. And the reason for that, if you remember back to the lecture where I was talking about the stack and the heap, stack was growing this way, heap was growing this way. Eventually, because the stack kept growing, it passed the space that it was allowed to store its stuff in. And we just ran out of memory to hold the stack, which means we tried to access memory we didn't have access to, and that is another way of getting a seg fault. Isn't that interesting? So well, technically, if you had a big enough memory, it would have been an infinite loop, but this lets it be a seg fault in this case. All right, so that is the idea. Let's uncomment this. And that was the first long example, but hopefully it made sense of this idea. So with that, let's now go to do the opposite. Let's print now, new problem P. Print from n to 1. All right, so I want you to think about this. Write down a recursive case, write down a base case. Do an example with n equal to 5, and then press play again. All right, so assuming n equals 5 again, capital N, let's write down an example. So we're going to print from n to 1 this time. This is going to, on our screen, we want to see 5, 4, 3, 2, 1. All right, when n equals 5. So where is the smaller problem this time? Find it. For this example, it's print from 4 to 1. Again, n got smaller, right? Interesting, interesting. So, all right, now we can break this down. So base case. Again, the base case is, it can be when n equals to 1 or n equals to 0, because eventually you'll have just print 1 or just print nothing. I like the print nothing case. 0, print nothing. And then the recursive case, well, yes, we're going to call our subfunction, we're going to call P on n-1 to print from 4 to 1. We're always going to do that, right? Because we need to solve that smaller subproblem. But look when it has to happen. In order to use this solution to solve the final problem of printing from 5 to 1, we had to print 5 first this time. Do you see that? So in order to make this call and have it succeed, we have to, right here, first worry about printing our n, which in this case, in this example, is 5. You see that? Because this is not part of the subproblem, and it's the first thing that needs to be printed. So we had to worry about printing our n before we made the recursive call this time. Interesting. Okay, so let me code this up. It's very quick, a quick change from this. I'll even include the comment, why not? This is print from n to 1, and this is all backwards now. So n minus 1, new line, n minus 2, new line, dot, 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 new line, 1, new line. Okay? So that's the idea. But the recursive case is kind of switched, right? Because first we got to print our n. So first print n, then call this recursive function, print from n to 1 of n minus 1. That's its new name. And we get to assume this works, and it'll print from n minus 1 to 1, right? As long as we used its solution to do the right thing on the bigger version of the problem. And that bigger version of the problem is solved by printing n first. So the only difference between this function and this function is the order of when the cout happens relative to the recursive call. And that makes sense if we're going to solve it like this, because we can't make the recursive call first, because we first have to print out our 5. That's not part of the smaller problem. Do you see that? So I hope this makes sense, and I hope you try and do this and write this problem out yourself. So like after this lecture, write these two functions yourself. See if you can remember how to do it and why it makes sense. All right. So that's the idea. And again, let's just call it at 5. This is from n to 1 of 5, and so we should see 1 to 5, n can't be negative, and then finally 5 to 1. Okay? And the reason this works again, I'm going to go a bit faster this time. Remember this definition. Here in main, which I will make tiny this time, we called first print from 5 to 1, which itself wasn't the base case, so it prints from 4 to 1 first, or it prints first the 5, and then it makes its recursive call, print from 4 to 1, okay, to do the rest. So right now we've printed 5 before we made the recursive call, which is very different to this version of the problem where we never started printing until we hit the base case. All right, so now initially we're going to print and then worry about solving the subproblem of printing from 4 to 1. All right, so now we're in 4, we're going to print our 4, and then print from 3 to 1, which is going to print 3, and then print from 2 to 1. That's the smaller problem, which is going to print 2, and then print from 1 to 1, which is going to print 1, then try and print from 0 to 1, which doesn't make any sense because we're going down. So it stops, and this does nothing. This is the base case. Oops, that arrow is not on the right spot. Base case. And everything else is recursive case. So this all just starts unwinding, and there's no extra work to do because all these functions now were waiting right here, and really they were just waiting to return. Okay? So now they've done all their work, and we have solved the answer we've solved the problem of printing from n to 1. Okay? So, before I get into more of these slides, let me just give you some brief math as to why this works. Okay? This is the key. Why? Because this should be your main question right now. Why in the world do we get to assume that the recursive call does the right thing? That is, as long as we build up the solution correctly. As long as we build up the final, larger solution correctly. Why in the world is this true? Let's look at it, though, from the bottom up. And this is, if you're a math major, or you've heard of something called mathematical induction, this is the reason why this works. We can use it to prove that recursion works. So here's our problem. It's called P. So assume we have a problem P, and we implement it. We implement an algorithm that is recursive to solve this problem. And so we'll have a base case, which solves the smallest version of this problem. And it doesn't have to be true that the base case always has like a size of 0, but I'll just say that this problem is called P of n, where n is a number that represents the size of the problem. So this will be like the smallest version of the problem. Let's say that means we're solving P of 0. And we can immediately give its answer. All right, so we have a base case, and then we have a recursive case. And using mathematical syntax, the recursive case is this. It's what's called an implication. It's saying that if you tell me, if I assume that I can solve the problem for one smaller of a size, for P of n minus 1, then I can use that. This arrow means using that idea to solve P of n. All right? So read this. That's math. Try to not have your eyes glaze over. It's kind of important. I won't be testing on this math or anything, but this helps you understand why recursion works, and you get to make these assumptions. So this is saying, assuming P of n minus 1, I can use it to or let's not even use the word assuming. Let's say I can use p of n minus 1 to get to p of n. And this is the idea of using that smaller subproblem to build up the final, bigger solution that we started with, the one that we were originally trying to solve. Okay? And so the reason that this works for any kind of problem, where this was like p of 5 originally, is this. I want to solve p of 5. Well, my base case gives me p of 0. Let's start from the bottom up. Let me put this over here. Let's start from the bottom up and see how this works. I originally had p of 0. All right, because the base case is true, we say. And I can use p of 0 with the recursive case, because I can have a previous problem that has been solved to solve one bigger version of the problem itself. So I can use p of 0 to get to p of 1 by starting with the base case and using one call of the recursive case. Okay? And then I can now have p of 1 at my disposal, which I can then use with the recursive case again to get from p of 1 to 1 bigger, because this is going from 1 smaller to 1 bigger. This is alternatively something like p of n implies p of n plus 1, if the original problem up here was p of n plus 1. And I should probably erase that because that's kind of confusing. But that's the idea. You can use the next smaller one to make the next bigger one. So this is the recursive case. I can use it again to get p of 2, which I can use the recursive case again to get p of 3, and again to get p of 4, and again to get p of 5, or as big as I want to solve this problem for, given the base case and given the fact that the recursive case looks like this, where you can use the smaller problem to build up the bigger one. Right? So this is why you get to make this assumption, because eventually, this is assuming that this works, eventually you're going to get to a case where it works. And then you can chain all of those ideas together to build up your final biggest answer. Okay? That is a lot of words, but hopefully, if you're a math person, that helps this make sense to you. Okay, so with that, let's move on now to talking about recursive data structures, because not just numbers allow for a recursive solution. Arrays can be thought of as recursive data structures as well. You can think about them non-recursively, so an array is just a bunch of stuff. So here's an array. It can be thought of as a bunch of stuff, or it can be thought of as one element and then a smaller array, because what is this array but its first element and a smaller array? Or, alternatively, what is this array but, you can break this down however you want, but this variable and this smaller array. So you can take the element out anywhere as long as the array that you're looking at gets smaller. So I guess technically you can take it out of the middle. It's like this smaller array, and then there's your one value inside of it. But we tend to just look at the front and the back as like that. So the smaller array can be at the back or at the front. And it's always, here's your smaller array, and here's the one element that you kind of took off of it to build that smaller version of the array. All right? So you can think of arrays as recursive. All right? And similarly, you can look at linked lists as recursive as well. But I think I want to give an example of using arrays recursively. And let's print an array recursively. I'll keep the same file. So let's print the array 2, 3, 4, 5 recursively. And by print recursively, I mean print the elements of the array. Okay? So what this is going to do, let's make our pretend function. Print array recursively. We're going to give ARR and its size, which is essentially 4. So I'm going to make my array. And then the size is 4. All right. Okay. So let's make this function. takes an array and its size. And remember that an array can be passed along using this syntax or this syntax. I'll use it like this, just to keep us on our toes. And then, all right, now it's our jobs to fill in this problem for this function. So the idea is, to solve this problem, we can choose to break down an array in any of these two ways. It'll work. So print array recursively. I'll use this version. So here's like the pseudocode for printing an array recursively. This is the idea. First, print the first element, then print the rest of the array. So this is our recursive case. Try to think of the base case. Let's just implement the recursive case first. So we're going to print the first element. And then we're going to print the rest of the array. How does one print the rest of the array? Now, this is a bit tricky. But remember that if this is an array, even though we can write it like this, that's our ARR, really, ARR is just a pointer to the first element of the array. So if we want to access this smaller array, we'll represent that as a pointer to its first element. How do we get to this? What's a pointer to this element right here? Well, it's ARR plus 1. Okay, see that? So the smaller array starts at ARR plus 1, and the size of that smaller array is size minus 1, isn't it? Whatever it was, minus 1. And this is good because the array is getting smaller. We know that. And so now that brings us to our base case. Base case should be the empty array, shouldn't it? Print all the elements in an empty array. How many of those elements are there? There are none. So print nothing. Nothing. All right, there we go. There we go. So I'll just say this. If size is equal to 0, return. Beautiful. And so now when we call this print array recursively, it should print 2, 3, 4, 5 in that order. And I encourage you to draw the stack diagram for making this work and understanding it. All right, so we print from 5, 4, 3, 2, 1. Now we print 2, 3, 4, 5, and let's just put a bunch of new lines in between all these, just to make sure that this is making sense. There we go. That's better. All right, so yes, this is printing that array 2, 3, 4, 5 in that way. And so I encourage you to draw the stack diagram for this and to understand why it's working. Okay, so that's arrays. We can also have a recursive description of the linked list, which I think I talked about a little bit in the last lecture. So again, you can think of it as just a bunch of nodes, one after another, or you can think of a linked list as a node and then a smaller linked list, just like an array. So like here's 1, 2, 3, 4. So like here's the first node, and then here's the smaller list. Do you see that? And you could represent this list, again, as a pointer to its first element. So like here's the new head of this smaller list. You see that? Whereas here is the original head to the first bigger list. Okay? So that's the idea. And yes, so I got ahead of myself. I think I put these slides in the wrong order. So I've already done this slide for you. We've printed the elements of the array recursively. Let's now do the sum of a linked list recursively. Let's see here. Nope, I don't want to show the answer. So let's make a recursive solution to the problem of finding the sum of a linked list. Okay? And so this problem needs to get smaller, and the way it gets smaller with linked lists is you call that problem on a smaller version of the array. Okay? And think about your base case. All right, so the recursive description of a linked list is its first node, and then a smaller linked list at the end of it. All right, so in this case, it's 10 is the first node, and then 50, 20, 40 is the smaller linked list that comes after it. Okay? So let's just set ourselves up for all this. Let's say touch rec list funcs.cpp for recursive linked list functions. I don't want to type all that out. And, well, we need a bunch of boilerplate. So let's have a main function. Let's include IOStream. What would really be nice if I could find that one file for linked lists with all those implementations of it. Ooh, there we go, there we go. Oh, that's what I'm talking about. All right, so here's our linked list data structure. And then, do I have a linked list itself here anywhere? Is this a simpler version of it? Yeah, something like that. Or I could just bring this all in. All right, so I'm just bringing in a bunch of code to initially make a linked list from a previous lecture. So don't worry about most of this if you don't want to. Dun, dun, dun. And I guess we need this insert to head of list function. All right, so I think that this should work. And now let's make 10, 50, 20, and 40. And so I guess I gotta do it backwards. 50 and then 10. And so this is now 40, this is now 20, 40, then it's now 50, 20, 40. Now it's 10, 50, 20, 40. That is the idea. All right, so we have a list, and we want to write a recursive sum function for this linked list. And, oops, I keep going to the wrong desktop. Let's, how do we want to implement? Yeah, let's just use nodes at the moment. So let's not pretend that we have like a linked list object that points to the head and the tail. Let's pretend that we just pass along a node pointer, okay? Recursive sum L head. Line. So this recursive sum function is going to return an int, which is the sum of the nodes, and we're going to give it a node for the head of the current list. And then I think that's all we really need. So this recursively sums the values of all the nodes in the linked list starting from head. Sums the data elements of the linked list starting with the node head. Okay? So in this case, we have 10, 50, 20, if I remember it correctly, that is 40, and here is our head. Okay? So when I call this function, just like I did, it set it up exactly like that. So we have a node pointing to the first element of this larger list, which has a head. Head's data value being 10. Okay? So with that, let's think about the recursive case and the base case. Dun, dun, dun. Let's see here. So recursive case, this is sum of linked list data. And so we have a base case and a recursive case. The base case is something, And the recursive case is a bit simpler to talk about. It's, all right, it's the sum of this smaller list, right? That's the recursive call. So the sum of the original bigger list is the sum of the smaller list plus the data value of the first element. You see that? So I want to add up all of these nodes' data values recursively. Well, I have to call this function on a smaller list. So I'm going to call it on this one, and that will give me, I get to assume that this gives me back 110. You see that? And then all I need to do to worry about creating the final answer to the bigger list is adding 10 to that. Okay? That's the idea. And then the base case is the smallest sum over a list. What is that? This is kind of getting a bit philosophical, but what does it mean to be at the end of a linked list? What is the base case there? Well, let's have it be the empty list in this case. It could also be the one element list, but the empty list is a bit easier. The sum of all the elements in a empty list. How many elements are there? 0. So what's the sum of 0 elements? The sum is 0. Okay, that's the idea there. So that's how we want this to work. We'll implement that in a second. But on this next slide, I have a bit of an implementation, but it's not completely finished. So please take a second to think about what happens when we run this code right here on this input list, with head being this first node. All right, so go ahead and think about that. And let's see, oops. I gave away the answer. So not really. What's going to happen here is, first, it's going to call the function sumList. This is the incorrect version right here that we're talking about. Let's say that we started from main, and we called sum on the list 10, 20, or no, it's 10, 50, 20, 40. Which then calls sum, because it's going to add 10 plus the sum of the smaller list, so it's got to call the sum of the smaller list, sum of 50, 20, 40. Which again is going to add the 50 to the sum of the smaller list, so it's going to sum together 20 and 40. Which is then going to add 20 to the sum of the list only containing 40. Which is going to add 40 to the list, to the sum of the list containing nothing, sum of the empty list. And this is the base case. This is what you want. And remember what happens here. Head, in this case, equals null. You see that? Head is null in this case. And you want this right here to return 0, but in this code, it's incomplete. It's going to dereference head and try to get its dot value. That's what the arrow does, dereferences, and it gets the dot. And then it'll also try to get its next as well. So it's dereferencing null twice, and the first time it does it, it'll fail and give a runtime error. So this program is going to crash, and I hope you notice that too, with the sig fault. The answer is B there. So that's no fun. And the way to solve it is to add that base case, because then this will finally return 0. Which will then add 40 to 0, which will then return 40, which will then add 40 to its 20, which was its first node, because it's always adding its first node to the sum of the smaller list. So this will sum up 40 and 20, so this will give back 60, and this will add 50 to that sum of the smaller list, which will then return 110. And this will add 110 to its original head node's data value of 10, and then it'll finally give back 120 to main, who can then go and print that out. Okay, so that's the idea there. And so we're almost done with this implementation. We just have to finally guard that base case. And so not head is the same as saying head is null. So because head would be 0 if it's null, and then not if that is finally something that's true. So think about this as equivalent to saying if head is equal to the null pointer. And I'll just go and implement that, and I think that's enough here for today, and we'll come back here on Wednesday to this slide. All right, so let's go and implement this. Here we called it sum list. That doesn't really matter. I'm calling it recursive sum. And it looks like we might have had nodes involving with double data, but I'm just going to use int data. So it'll be int sum here. And we don't say value, we say data. We say data and next for our implementation of nodes, and the name of this function is recursive sum. All right, and so this not head is equivalent to saying if head is equal to the null pointer. Okay, return 0 because that's the sum all the nodes in an empty list. Ooh, this indentation is a bit weird. That's okay. This is the recursive case, where we'll sum the smaller list. That's in this recursive call. And remember that we get to assume that that works for us, and then build up the bigger answer on the larger list by adding our heads data, because that's what we didn't consider in this smaller list here. Okay, and that's the final sum. So hopefully that makes sense with this stack diagram. And let's just have this run. So recursive sum of this list 10, 50, 20, 40 should, in theory, do everything that we talked about, draw that stack diagram in memory, and it'll all work out. And it prints out 120 to us. Beautiful. Okay, so that is what I wanted to talk about today. We'll come back to this slide next time. We'll come back to here. I don't want to give you a 1,000,000-hour long lecture, the lecture after the midterm, so we'll stop here in terms of information. But I first, before I go, I want to talk about a few things from your next lab and also your next homework. So I've extended all these things, by the way, because of your midterm. So on homework 8 and lab 7, I want to talk about some stuff. Oh, I had that open. Cool. So for homework 8, there is this delete node function, and you might be wondering if this syntax is a typo, and it is not. So let me talk about that just briefly. It is both a reference and a pointer, so it's a reference to a pointer. The struct is optional. We don't use that in this class usually, but you could have just said node star ampersand head. The reason this is necessary is because you might want to delete the head, and that means the head needs to change. So, not a typo. Head is a reference to a node pointer. Okay? Read it like that. This is a lowercase head. This means that the head variable, if you reset it, changes the variable from another function, usually main. Let's say main here. Changes that variable inside of main itself. That originally pointed to the head of the list. So the idea is, let's say we had the list, I don't know, 1, 2, 3. And you wanted to write a delete node function that originally head was this. We want to delete the value 1, perhaps. if we deleted the 1 node, well, the head of the list should now be this right here. So we would have to say something like head equals head next before we did the deletion, of course. And the reason we want to do that is because back when we come back to main, this head should now point to a valid list. And if we weren't able to change it, so if we didn't have this ampersand, if we weren't able to have a reference to it and actually change the original head variable, then that old head variable would still have been pointing to this node that is no longer here, right? So that's the idea. We want to do that. And I've already explained this from last time. And then just briefly on Lab 7, I want to talk about 2 of the functions that you'll implement. They're a bit difficult. So add into start of list and add into end of list. Technically, we've already done this first one. You'll have to think about this one as well. But let me just draw some examples for what you're going to be doing in code. So here's your list, like L is your list. And it points to a linked list object, which holds a head and a tail. And here is our list, 1, 2, 3. All right, if this is our list, what you're going to be doing in the add into start of list function is the following. I'll actually copy this so that I can do it the same for the next one. So if we're going to add a node to the start of the list, we have to do a few things. Oh no, don't change the color. Thank you. There we go. Oh my. There we go. So if we're going to add an int to the start of this list, well, this is what needs to happen. We need to make a brand new node. Maybe it holds 0. Set this pointer to the old head, remove this pointer, set the new head pointer there. And also, this might need to change if the list was initially empty. Okay, so think about that. And then adding an int to the end of the list, let's say we want to add 4. What needs to happen here is this list's next pointer, which is the tails originally, its next pointer can't be null anymore. It needs to be pointing to this new node. And this new node that we just made, which is now the new end of the list, has to have a null tail pointer. And again, this tail pointer here, or this is the next pointer, sorry. And then this tail pointer needs to now point to this new node because it's the new end of the list. And possibly, if the list was initially empty, dually, it'll have to be changed to be the first one as well. Okay, so just think about all those cases. I just wanted to draw this out for you so you can see what needs to happen. Some pointers need to change and get reassigned, and some pointers need to be initialized to the correct value so that the list stays intact and goes in order. Okay, so those are the 2 things that I wanted to talk about for the lab and the homework. With that, I think that's everything that I wanted to say. We will continue on this slide next time, so I'll see you then.